What I'm trying to show today is how some kind of new tools that have been developed in the last 15 years can be used to solve some inverse problems, and especially the problem of unmixing features. So, mixing is, you observe, for instance, several features, 2 signals at 2 different frequencies plus 2 bumps, and what you observe is just the sum of all of them. And what you are interested is to recover the different features. If you work with the images, another example is here, you have Gaussian and lines, here, and you want to recover the lines and the Gaussian separately. So this is very similar to the problem that we have seen this morning about extracting the lines in the images and towards nodes and artifacts and everything. So that's another kind of problem. And in fact, we are faced with this kind of problem very often. To give you an idea, so here is a Gemini image, infrared image, and you see all these striping effects, which are due to the detectors. And all these stripings makes very difficult the detection of a galaxy which is at the center of the image. For instance, if you are using the extractor on this image, you are not detecting the galaxy. Another kind of problem is supernovae. So you are working with supernovae, so we have one image of the whole galaxy, and you re-observe many times the same object, and you make the difference between the reference image and your new image. And then you try to detect supernovae. But then you start to have problems when you have this kind of feature in the image, which is quite often, and then at the end in your detection catalog, here's what you get. So many spurious detections. So this kind of artifacts can be seen as an additional feature on top of the image that you want to get rid of. Sometimes you have some different kind of scientific interest in the same image. For instance, this is a Herschel image, and here the goal was to extract the filamentary features in this image in order to study how the stars are forming along the filament. So how can we separate the stars from the filament? This is again a problem of mixture. For LSST or other kind of survey, what you have very often is several bands, and each band you have some kind of red and blue galaxies. So we have typically several bands like that, and you want to separate them blindly. You don't have any information. So you can formulate the problem of mixture, or unmixture if you prefer. Like this, for instance, you can have one image or one signal which is the sum of several components that you are looking for, or you can have several channels. So I is the channels number here, and where each one is a mixture of several components, and here is the point spread function of the instruments. So the convolution with the point spread function of the instrument. And again, here at the data, N is the noise, and you are looking for the different components. Sometimes it's even more difficult because here we can assume that we know A, for instance. We know that's the spectrum more or less of a red galaxy or blue galaxy. But for other cases, we observe a mixture of many things, but we don't know how the mixture is done. We don't know this A coefficient here. So this is even more complicated because you have to find both the sources, the elements, and the way that they are meshed together. So this is even more complicated. So typically for SKA image, if you want to find the signal of EOR, then you have to solve this kind of problem. And that's no other way to escape. A typical problem, similar problem is the Planck problem. So Planck, everybody has seen the beautiful images. You observe in 9 channels, the sky in 9 channels, and each channel you observe a mixture of many things, which is the cosmic microwave background, but plus extragalactic signals plus galactic signals, and you want to separate this cosmic microwave background from all the other parts. So this is a kind of tough problem. It's even more difficult because what you have also is a difference of resolution between the different maps. So there is a difference of 5 in terms of resolution between the best map and the worst map. So you need to take into account this different beam in the problem. And Planck is even more difficult because the mixture is also position dependent. If 2 pixels, so the same component, for instance, the dust, have a spectral index which is different from one position to another one. So it means that the mixture is sky position dependent. So here now we have the pixel position here, which is here. So, and this makes the situation very, very complicated. Because there are much more unknown by a huge factor than you have there. So how to solve this? So you can write all this problem in a kind of unique framework where you have wide the data, can be monochannel or multi-channels. H is a big operator, and you need to solve this problem, and you have not a unique solution, because you have much more unknown. When you have 2 images and 1 observation, then you have 2 unknown and 1 observation. So it's not easy to find the problem, and you need to have some constraints. And the constraints are the key points. You need to have the right constraint, a good constraint, in order to get a reasonable solution. And the whole game now is to play with the constraint. So people have heard maybe about maximum entropy. This is a very old and famous method. This has a kind of constraint that can be put in order to solve this problem. So for Planck, how did they proceed in order to solve this very, very complicated problem? First, they had to deal with the difference of resolution. So there was two kind of methods. Some of the methods, they just downgrade the base map to the worst resolution, and some others, they convolve to the base resolution the bad maps. But then you have the node which is blowing up, but you have to deal with that. And then you need to have a way to constrain the solution in order to get the CMP. So the first one is to assume that you have a full modeling of the sky, and this is the commander ruler technique. And so you assume that you know the probability of the dust and you know the probability of the different emission, and then you try to fit the parameters of your model using kind of Bayesian technique like an MCMC. And this is quite complicated because first the model is very crude. You have only an imperfect knowledge of the dust and synchrotron emission and everything. So it's not so easy to have a right model. And the second point is, because these are very intense in terms of computation time, these techniques are not done at the full resolution. So in practice, the way it is done is you have a model at low resolution, and you interpolate the parameter of the model to the full resolution. That's the way that this Bayesian technique is working for Planck. Another technique which is quite famous in astrophysics is template fitting. So we have 9 channels, and you can maybe assume that one of the channels is a good template, and then you subtract this channel to the what you call cosmological channel. And this is the template fitting techniques. And the 2 other methods are based on what is called internal linear combination, which is a method which has been used for WMAP. And here the idea is to assume that you can look at the data, one component which is CMB plus multiplicative factor, plus some residual which can be considered as Gaussian. Okay, in practice it's not Gaussian because dust emission is not Gaussian, but you can assume it's Gaussian and then you get some linear discrete estimator and you get this kind of relation and you can get this map in this same way. There's 2 ways to do it, in the Welle domain or in the spherical harmonic domain, and then you get 2 different solutions. This estimator is quite very famous in statistics, it's called the blue estimator. And each of these methods has some limits, as any method. And here are the results on the WMAP, but for the 2013 release. And you see that all the methods are quite good, but when you are becoming close to the galactic center, then you start to see the limit of the method. Because then the mixing matrix is varying very quickly. So it's any approximation, you pay it when you arrive close to the galactic center. So in practice, to do some analysis, the galactic center is masked. For instance, for cosmological studies, 30% of the sky is masked before the analysis. And for public release, because this is not very nice to see, you have masked the galactic center and you call what you call it inpainting. You fill the gaps by something which looks like real data, but which is not real data. And that's what has been released to the public. So now this all these techniques are either based on a model or on pseudo statistics or some very crude template theory. In the years 2000, there was really a shift of paradigm in the signal processing community or statistics community in the way to handle the signal. And while we have been using for years and years the channel theory, discrete estimator, and non-limited signal as a model, the new way to interpret the signal is to use the comparison theorem to have a new modeling of the signal, which is sparse signal, which is not band-limited, and to use other norm to minimize the solution, which is L0, L1 norm. And with these new ingredients, we have a really new way to handle inverse problems. And now I'm going to show you how, using this idea, you can solve differently the problems and get all the solutions, which are quite good. But I don't know if people are aware of sparsity. I just make a small introduction. Sparsity is the model for a signal. We say the signal is sparse if we can represent it in what you call a dictionary. A dictionary is a set of functions. For instance, the Fourier domain is the most well-known dictionary, where each function is a sign. So the idea is to have a signal which can be represented into a dictionary phi, and then you get some coefficients. So if phi is a Fourier transform, alpha is a Fourier coefficient. Okay, so in the case of the Fourier transform, it's very easy because you have a fast transform which goes from S to alpha and from alpha to S, which is an inverse Fourier transform. But you can have other dictionaries, so wavelets are quite well known. So you can have a wavelet dictionary. And the point is, you will say that the signal is sparse in a given dictionary if, when we sort the coefficient from the largest to the smallest one, the absolute value of the coefficient, we have a fast decay. As soon as we have fast decay, we say that the signal is sparse in this dictionary. What means a sparse decay? It means that most of the energy is contained with few coefficients. Okay, so if you look at the histogram of the coefficients, alpha, then you are sparse when you have a kind of non-Gaussian behavior. You have a kind of Laplacian distribution here, and the tail of the distribution contains most of the information, because the coefficients which are in the tail are the most energetic coefficients. So everything is in the tail. So here we are completely considering high-order statistics. What you are interested in is not the two-point statistics or the kind of thing. It's really the kurtosis, what is in the tail, and what it is here that we have the important information. To give you a clear idea now what it is, here is an image. You look at the histogram of this image. It's completely not sparse in the pixel domain. You go in the curved space, which is a kind of wavelets. Here's what you have. So just changing of space of representing the data, you see that you have a different behavior on the coefficients. And now if you sort this coefficient, here's what you replace from the largest to the smallest one. If you take this image and you take only the 1% is the highest value, here as this pixels. So here, with 1% of the largest coefficients in the pixel domain, you have something like roughly 8% of the energy of the image. Now you do the same in another domain. You go in the wavelet space. And again, you take only 1% of the coefficients. You set all the others to 0, and you reconstruct the image. And now, this is the reconstructed image from 1% of the coefficients. And now we have 99% of the energy. So you see that this 1% of the coefficients, you have a rather good approximation of the image. And that's the whole idea of sparsity, is almost all images, and I said all images, if you take a picture of this room, you will be sparse in a given domain, and typically wavelets, curvelets, or these kind of dictionaries provide you sparse transform of the data. And then you can use this behavior of all images that they are sparse, which is almost as true that any astronomical images obtained by a telescope is positive. You can say also it's sparse. Then you can use it to solve inverse problem. And the way to do it is now you have this inverse problem to solve, y equal hx. X is your unknown, y is your data. and you will say that x can be represented in a given dictionary phi. So you have x equal phi alpha. So what you have to solve now is y minus h phi alpha. And what you will say as a constraint is that your alpha coefficients are sparse. And to constrain the sparsity, here comes this L1 Z0 norm. In fact, there is some theory which shows that P has to be below or equal to 1. As soon as P is equal or below to 1, we reinforce the sparsity of the solution. So now you cannot, with this kind of equation, and the last 10 years has been a new field of optimization appear to solve this kind of equation. So we have many new algorithms. And the one that we are using in our program has been only published 2 years ago. That's a very active field at this point, optimization theory to solve this kind of problem. So what we have here is the inverse problem where you have y equal h phi alpha. And here, another important point of sparse recovery is that there is a lot of theory behind. For instance, if alpha is sparse enough and h is random, then we arrive in the complex sensing framework. And we know that solving this equation not only is a good way to regularize the solution, but it goes exactly to the right solution. So it happened that there are many more theoretical papers which show that for a given class of operators and a given class of signals, then we know that solving these equations leads exactly to the solution. And this is a kind of very strong argument for sparse recovery, because there is no other regularization penalty in math that where you can have this kind of claim. If you use Markov-Random field, maximum entropy, partial differential equation, any kind of regularization term that you are using, you have never a claim that for a given class of signal you get the right solution, the true solution. Okay? So this is a kind of very strong argument which made the sparse recovery is so large. People are using sparse recovery for almost everything. So you can see for denoising, deconvolution, blind component separation, painting, minimization technique. You can go in any domain from geophysics to biomedical imaging, astrophysics. People are using sparse recovery because it's very efficient to solve inverse problems. So now we write the equation here. So there is two ways to do it. So very often we use a Lagrangian formulation, which is written this way. So we have now this lambda parameter which arrive, or we can write it in the what you call the analysis form. And now we express everything from x, but now it's a transformation of x through this sparse in the dictionary. So there are three main ingredients here to solve this kind of problem. The first one is the choice of the dictionary. The second one is which minimization technique you use. And now there are tons of minimization techniques. And the third one is how to fix the regulation parameters, which is important. So I'm not going to, in this talk, to enter in the technical details. I'm going rather to show you some results and how, what kind of result you can get using this kind of techniques. But clearly, the sparse recovery technique you will have to choose these three ingredients, and the way that you select each of them will provide you one solution. So now, the dictionary, very often we are using wavelet transform in astrophysics because wavelets are very good for features which are more or less isotropies. So if you are looking for an isotropy feature, you can use curvelets. So curvelet dictionaries, the elements in the dictionary are elongated, and they have different elongation, different size, and you can decompose on curvelet coefficient exactly as on Fourier and on wavelet you can decompose an image and reconstruct from the curvelet coefficient. So you have many kind of dictionaries which already exist, and here also there is a kind of connection between machine learning and sparsity, because you can also learn the dictionary from the data. Imagine that you have a training set, simulations, or whatever, or even from the data themselves. You can learn what are the best shapes for your data. And that's what we call dictionary learning. And here there is a clear bridge between the machine learning community and the sparsity community. So, the only thing you have to remember here is you can design a dictionary, and here it's our choice. As physicists, we know that we are expecting galaxies which are more or less isotropics, or you may have some jets in the data, so you may prefer curvates. But clearly here is a kind of prior that you put in your data when you choose a dictionary. And you have to be aware about that. Nothing for free. So now, example of applications. This is what we call morphological diversity. So now we have a model for the data where we say that the data is a sum of several components. For instance, two components. One are isotropic and the other one is anisotropic. So this is a Hubble Space Telescope image, and now we are going to try to remove blindly what is anisotropic from the data. And so you come up with this kind of equation to solve, where you say U1 load is a sum of two components, or three, and you want to minimize this equation, so the sum of the two components should be close to the data, but each one will be sparse in a given domain. So there is a constraint for the first component, a constraint for the second component, and you will say that the first one will be sparse in the wavelet domain, and the second one will be sparse in the cloudlet domain. So here what we are trying to do is to use the fact that the two features we are interested in have different morphology. And the way to use this information of different morphology is to say that if I have a galaxy which is isotropic, it will be very sparse in the wavelet domain, but not very sparse in the cloudlet domain. While if I have an arc, it will be very sparse in the cloudlet domain, but not very sparse in the wavelet domain. So using sparsity as a constraint, you can separate the two. Okay? And to come back to this image I showed you before, so this is a simulation, line plus Gaussian plus noise, and here we separate blindly, using this minimization technique, this image into two components, the Gaussian and the line. And this is done completely blind. Just say I have one dictionary which is wavelet and another one which is curved. And that the coaddition here of the two images, and here is the difference between this image and this one. That's the residue. So that's a way to make a blind separation without having to detect anything directly and to separate it. It's really the minimization algorithm which makes the separation for you. Now coming back to the gravitational arc, here is what it is here. So here we have three components, widget, curvates, and here is the sum of the two. And here is the wavelet component. And you see that not only we have removed the gravitational arc, but also all the arclets which are here. So somewhere it's quite interesting to make this kind of separation. So now coming back to the artifacts. So Gemini image. Okay, so here again we have those three dictionary, widgets, curvates, and wavelets, and blindly here we were able to find the galaxy. So the sex factor was not able to detect the galaxy on this image, but if you make the separation, then it's obvious that you have an object here. So again, here sparsity helps to disentangle between different components. Some of them are just artifacts, and some are real, something interesting in the sky. So now we can consider these are just artifacts, so we can combine them and subtract from the image. And now here is what we call the clean image. So we have just removed the artifact from the image, and you can start to processing, co-adding this image with something else, or whatever, but then you can consider that you have removed the artifact from this image. So for the Herschel data, in fact, it was the same tools that we use, curvets and wavelets. Curvets because curvets are good to extract filaments, while wavelets are good to extract stars. So we were using this image and separated one image into two parts. And doing this, we get these two images. And then my colleague at Starck, Philippe André, who is a specialist of star formation, have been able to build a model of star-forming objects along filaments, thanks to this decomposition. So that's a way to extract some more meaningful information from the data. And you can also do this in 3D. For instance, this is an example of a simulation where you have shells and Gaussians, and you separate blindly using what you call beamlets in 3D and Gaussians here. Okay. The last example in one Gaussian example was this artifact on supernovae, and this is a very recent paper that we just did. So we have seen that when we have this image, we have a lot of artifacts, and all these black ones is supernovae detection here. So you see that a huge amount of skew detection. But now, starting with from this image and using this morphological, sparse morphological diversity, separate it into several parts. Now from this image, we were able to go to this image. And again, this is very interesting because now you have much less purification. And using these techniques that have been shown in this paper, that you can divide it by 2 the amount of purification just by using this pre-processing. So that kind of technique that can be very interesting for artifact removal. I'm not sure that you can do it in 1 second. So for LSTM, I'm not sure that it works. But if you have time, then you can optimize your processing and for a given image at least get some nice results. So now from mono-channel to multi-channel. So here we have some data, that's real data, and you have some red and blue galaxies. They don't have the same spectrum. Okay, all blue galaxies have somewhere a slightly different spectrum, but they have a kind of more or less same ACD. So we have a kind of average ACD for blue galaxies, average ACD for red galaxies, and we consider that the mixing matrix is this ACD. Okay, so we just merge using, we assume that that's the model. It's a bit crude, but in fact, even if it's crude, that will be worked, and we have been able blindly again to separate red galaxy to blue galaxies. So this is the red galaxy and this is the blue galaxy. So here we have seven bands. Each one was containing blue and red galaxies, and we have just separated them blindly. So that's kind of other thing that can be very useful. So now, coming back to Planck, I told you before, we want to remove all the foregrounds from the data, and can you use sparsity as well for that? And the answer is yes, you can do again sparsity. And here now you have this problem to solve, but as I told you, this matrix is unknown. So you have to find at the same time the matrix A and the source, the different sources, especially the CMB. In practice, it's not completely blind because you have one column that you know, which is the CMB column. It's a column from the dust and from other components that are unknown. But the right term will be semi-blind deconvolutional way that you have to do. And the way to do it is kind of iterative techniques where you estimate first the matrix, then you estimate the sources, and you iterate again this way. And the way it works is we start from the largest coefficient, and we have a first estimation of the matrix from the largest weighted coefficients. And then when you have an estimation of the matrix, you re-estimate the source, and you decrease the threshold, and you take more coefficients. So it's a way to make the separation from the starting from the most important coefficient in the data, and then slowly and slowly taking more and more coefficients from the data. And here, to take into account also the behavior of the beam of the instruments, we use wavelets, so we make a component separation per wavelet scales. And to take into account on the fact that the mixing matrix is very spatially, what we did, we made a partitioning of the sky. So we decompose each wavelet scales into patches, and we apply a component separation on each small patch. So it means that we had one mixing matrix per patch and per wavelet scale. So a lot of mixing matrix. So it's a kind of complex modeling of the data. But at the end, we remember the 4 maps that have been delivered by Planck. Here is what we, and for large-scale studies, they were masking 30% of the sky. And here is what you have using sparsity techniques. So here, there is no inpainting. Okay? So what we are able to provide a full sky CMB map without doing inpainting. And this was what, I think that was the first time that we can break the galactic barrier and to recover the CMB everywhere. In a study, we have shown that more than that, for large-scale study, we don't have to mask at all. We can keep all the data. We even show that masking is even worse than everything else. Because if you mask more than, I think it was 20% of the data, then you lose the information at the larger scales. It has a really masking more than 20% of the data has a huge impact on the quality of the analysis. And this is why we have kind of nice results. So just to show you what's going on in the galactic center, this is one ILC image in the Webber space. So you see all these artifacts in the galactic center. This is a template feeding technique. This is the kind of ILC in the spherical harmonic domain. So here they do the kind of diffusing painting. So they diffuse the border of the mask. And here's what you get using sparsity. So you see that it provides quite nice results. That was on the planned release 2013, and that's the last release in 2015, so this year. And here you see that they are quite similar. The commander map looks very nice, but again, they are inpainting the map, so it's hard to say how they can do in the galactic center. But then just, this is very recent result, I think like last week result, not published. We did the same on GMC, the GMCA, the sparsity techniques, and here is the map that we have. There is one interesting feature in these maps. There is one, it's very hard from real data to assess the quality. But there is one thing that you can really easily assess. Is the contamination with what you call the clusters. Because there is one channel, the 217 gigahertz channel, which is free of cluster. Because the spectrum of the cluster cancels and this frequency. So if you subtract the 270 channels to the CMB map, you should never see the cluster. And that's a very fancy, very standard and straightforward way to see contamination by the clusters. So you go, you look at a given specific place, like the coma space, where there's a strong cluster, and you make the difference. And here's the difference between the four CMB Planck consortium maps, and this is what you get using our map. So you have you have completely cleaned the cluster effect, what you call the Senel-Zeldovich effect from the CMB map. Why? The four Planck maps were contaminated. So we also have derived a kind of other way to assess the quality of the map using kind of non-Gaussian tools. So I'm not going to go into details, but the thing is, more it's red, worse it is. So more it's blue, more it's the dark blue, better it is. And you see that you see all the artifacts of the component separation technique in the galactic center, while using our sparsity techniques really help for that. So here, what I show you is, if you open your mind, you have new tools in math, new optimization techniques, then you can have completely new solutions which are completely different to anything else you have done. It has a huge impact for large-scale study, because now we have shown that you don't need at all to mask the larger scale. And more than that, if you mask, you kill some information which is quite important. So you have here, if you have better data, you need to be smarter. You don't need to mask more, right? Not because you have data that you have to kill 30% of the sky. You make a full sky survey, try to get the best you can using the smartest tools in math, deep learning, machine learning, whatever. You have to try to get the best that you can, the best from the data. So to conclude on this sparsity and CMB, I said that what you have here is a very nice way to handle with the component separation and to separate the CMB from the other part. We have a very clean CMB map which is available on the web, and we did some study on larger scales, and you saw that it has an impact on the larger scale. We also, I didn't show it here, but we have also a nice recovery of the pyramidal power spectrum, and everything is available: paper, software, and data. Everything is there. And one important feature of what you have done is what you call reproducible research. More and more, I think it's important, and I'm sure that people in SSC are very aware about that. It's very important that you can reproduce the results. It means that we need to know exactly how a given plot in the paper has been produced, and everybody should be able to reproduce this plot. And here what we did, we not only provide the software, but we also provide the script reading the data and providing the results. So we provide everything: the script, the software, and the results. So everybody can just reproduce our map very easily. And I will say that it's the only CMB map which is reproducible from blank. The others are not reproducible. Nobody knows how to derive a CMB map that can be published. So to conclude, I will say that sparsity is very efficient for component separation and more generally for inverse products. Every time you are looking for features embedded in nodes, sparsity is very useful. Because in fact what you do when you do sparsity, you cross-correlate the C node with many shapes. And you know, everybody here certainly knows the match filter theorem. If you want to detect a feature, the optimal filter is the feature itself. Okay? But you cannot cross-correlate the data with all features in the universe. So you have to make a sub-selection of the feature. And this sub-selection of the feature that you are looking for is what you call the dictionary. Okay? So in fact, sparsity is a kind of generalization of the match filter value. You don't know the filter. And you have many shapes. And you can select wavelets or curvelets. And this is kind of prior. You have the physicist, so you should have an idea what is in your data. And doing this, you have some modern tools, and you know how to minimize properly L1 norm, which reinforce the sparsity of the solution. We have a lot of theory which is already exists, and it's also a domain very active in applied math and statistics, where from given operators or given class of signal, one can claim that you have a true solution of the problem, or a solution which is bounded by the noise if you know the noise, or this kind of thing. There's a lot of theorem already in the literature. So there is a lot of theory which supports sparsity, which doesn't exist for any other penalization term. Another important of what we have done is research, as I told you. And for us, the perspective is to extend to polarized data now, and also to extend this kind of technique for SK and UQ. This is ongoing work. To conclude, I will say also that sparsity can be also linked to Bayesian statistics, so it's not something which is completely independent. Sparsity also has some bridge with machine learning, and I'm expecting the future to see this bridge becoming stronger and stronger. So, and sparsity has also this compressed sensing theorem, so I didn't speak here about compressed sensing, but there's also many things you can do with this new theorem. And the design of instruments directly linked to the reconstruction of the data start to be something quite important in general. So people are thinking more and more as we are building an instrument, but we have to consider at the same time the way to sample the data and to reconstruct the image. And you cannot separate anymore the design of the instrument and the algorithm for the reconstruction. Thank you.